Good evening and good morning to the HotChips attendees around the world. I'd like to thank the HotChips conference and the tutorial organizing committee for inviting me to present AMD's view on how advanced packaging will enable the next generation of Moore's law scaling through the use of novel heterogeneous interconnect architectures. As has been widely documented, Moore's law is slowing down, and cost per yielded millimeter square of silicon area keeps increasing with node progression, as illustrated by the slope of the curve changing around N7. In parallel, die sizes for high-performance computing are also growing rapidly beyond reticle size limits. The bottom left chart indicates the die sizes of server CPU in blue and GPUs in red over the last decade. And the breakdown of Dennard's law means power for high-performance computing also keeps increasing. Bottom right graph shows power of top 100 supercomputers in the world increasing from about 1 megawatts to about 10 megawatts in less than a decade. All of these challenges are coming in at an exponential rate to keep pace with the insatiable demand for computing, especially in the high-performance computing markets. So, compute demand is increasing, but needs to overcome significant barriers to traditional Moore's law and Dennard's law scaling, once again illustrated by the server CPU and GPU die size charts over the last decade. The second chart illustrates the bits per year projected for CPU and CPU-GPU markets and is growing at an unsustainable rate, driving the need for domain-specific accelerators. Accelerators can enable more performance within the power budget, cost, and other constraints, but it can also lead to potential new complexities for highly accelerated, highly heterogeneous systems. Every system architect is going to solve different problems using different data, different end product requirements, and industry drivers, which brings us to the future of computing as being defined by modular designs driven by the era of advanced packaging. A quick background on chiplets. Historically, Moore's law enabled sufficient scaling to satisfy computing demands except for very large systems. So, we were able to design a die and then put two of them together to get approximately 2x performance. But with Moore's law slowing down and performance needs increasing at exponential rates, the traditional approach for growing die sizes is not sustainable anymore. This requires a new approach with chiplet-based architectures to continue scaling for high-performance compute demands. But the challenges with chiplets are multifold. Additional I/O area, additional design effort and complexity, as well as the requirement for new methodologies in design, test, assembly, and sort. The transition from monolithic to chiplet approaches is illustrated in this slide. The key value with chiplets is that they are able to provide a scalable path to enable many more functional SoCs due to the ability to yield many more die within a given wafer. This is illustrated in the difference between the bottom of the slide showing increased number of functional SoCs versus the top of the slide, showing reduced number of functional SoCs. Chiplet-based architectures also provide better known good die, as well as an ability to mix and match at finer granularity on the package. They also enable productization of the same die across different market segments, as demonstrated in the Zen 3 core compute chiplets being used across server and high-end desktop markets. Hence, modular designs can be seamlessly enabled with the use of chiplet-based architectures. AMD has been down the modular design path for many years now, enabling industry-first 2.5D HBM and multi-chip module to enabling chiplets in mainstream EPYC and Ryzen, as well as our recent introduction of the 3D chiplet architecture at this year's Computex. Modular designs with advanced package architectures needs to focus on a few key parameters. First and foremost, cost and volume manufacturing capability with scalable, cost-effective solutions. Second, bandwidth density at minimal die-to-die interconnect overhead, as well as energy per bit to reduce the die-to-die power. The key focus areas in silicon package co-design are performance, power, area, and cost, or PPAC for short. These determine the choice of the type of package architectures that can be paired with silicon nodes for specific product implementation. Chiplet-based package architecture definition is more nuanced since we need to figure out how to enable the best PPAC by using the appropriate heterogeneous architectures for configurable segment-specific optimization, since not all products can be bound by the same PPAC requirements. The other goal is to maximize product yield by enabling smaller chiplets without significant interconnect overhead. Since with standard packaging techniques, I/O can consume a large area on the silicon, which can be extremely cost ineffective with silicon node scaling. AMD collaborates with our ecosystem partners with a view toward continually expanding our advanced packaging toolbox to enable our chiplet roadmap with tighter integration schemes to be able to scale into high volume markets. Many package architectures exist in the industry to enable die-to-die interconnectivity across the various product segments from mobile to PCs to server and desktop. Examples include MCM architectures from AMD and other industry players, other 2D architectures based on RDL interconnects or 2D organic like InfoR and Focus, 2D silicon-based architectures like EMIB, InfoLSI, Silicon Interposer, where the die-to-die interconnect is achieved using a passive silicon, as well as 3D architectures defined as active-on-active silicon stacking. Foveros, wafer-on-wafer architectures found in image sensors and the memory markets are some examples. Chiplet package architecture choice is not a one-size-fits-all approach. Rather, the choice is made based on specific PPAC requirements per product. Two-D package architectures are typically less expensive than 2.5D and 3D architectures, while 3D architectures provide the best interconnect energy and bandwidth efficiencies. Due to the challenges noted, chiplet-based package architecture definition requires balancing a complex trade-off. The value of the modular product being architected, plus the associated chiplet yield and technology scaling benefit, should be more than the I/O silicon area overhead, plus packaging cost adder, plus power cost of the interconnect, as well as cost of the engineering complexity of the resulting solution. Hence, this becomes a multidisciplinary optimization exercise across organizational boundaries. Our investments and innovations in packaging have been a multi-year, multi-technology journey. AMD introduced high bandwidth memory and the 2.5D silicon interposer technology to the GPU market in 2015, which led the industry for best memory bandwidth in a small form factor. We then set a new performance trajectory for compute in the data center and PC markets in 2017 with the introduction of multi-chip module packaging. In 2019, we introduced the industry-first chiplet-based technology using different process nodes for the cores and the I/O in the same package, which enabled significantly higher performance and capabilities. At Computex earlier this year, our CEO, Dr. Lisa Su, announced the next big step in our continued trajectory in pushing the limits of advanced packaging, 3D chiplets, that we have pioneered in close collaboration with TSMC. This architecture combines our chiplet packaging with die stacking to create a 3D chiplet architecture for future high-performance computing products. AMD's packaging roadmap is shown in context of the IEEE heterogeneous integration roadmap metrics, namely the linear interconnect density on the left y-axis and areal interconnect density on the right y-axis in a logarithmic scale. Linear interconnect density refers to the number of interconnect wires per millimeter per layer that can be escaped on the SoC edge, and is a metric for 2.xD architectures and is represented by the gray colored line. The scale goes from 1 to 1000 wires per millimeter per layer. Areal interconnect density refers to the number of wires per millimeter square of the SoC area and is a direct function of interconnect pitch and is a metric for both 2D and 3D architectures and is represented by the orange colored line. The scale goes from 10 to 100,000 wires per millimeter square. Performance, power, and interconnect area typically scale moving from 2D to 2.5D to 3D architectures. With 2D MCM, 2.5D silicon interposer for HBM, and now the 3D chiplet-based architectures, AMD's advanced packaging roadmap now covers the entire interconnect density portfolio to enable high-performance computing products. Next, we get a little deeper into our 3D chiplet architecture. We are using an industry-first hybrid bond plus through silicon via approach that provides over 200 times the interconnect density of 2D chiplets and more than 15 times the density compared to existing 3D stacking solutions. This enables a much more efficient and denser integration of our IP. The die-to-die interface is using a direct copper-to-copper bond with no solder bumps of any kind. This approach dramatically improves transistor density and interconnect pitch over other 3D approaches, and is perhaps the most flexible active-on-active silicon stacking technology in the world. With the tiny through-silicon vias and the direct copper-to-copper connections, this technology consumes less than one-third the energy per signal of microbump 3D approaches. This is truly a revolutionary technology that is a key part of how AMD will push the envelope in high-performance computing over the coming years. Now, we dive deep into the die floor plan over the SRAM region indicated by the purple area, where the TSVs are inserted to illustrate the interconnect density differences between standard 2D MCM or C4, 3D microbump, and TSV-based architectures. In the upcoming video, I encourage you to focus on the purple swath and pay close attention to both the dot and the hypothetical effect it would have on the area of the purple swath to see the impact of enabling a hypothetical C4 and microbump architectures followed by our implementation of the TSVs. If we had enabled the 2 terabytes per second SRAM bandwidth between the SRAM and the CCD with standard C4-based interconnects, we would have spent a lot of silicon area, as you can see in the huge swath of purple space on the die. Microbumps increase interconnect density marginally, but would have still taken up a significant area. The size of this interface is dead silicon, which is not cost or performance efficiency for the non-stack products, where we utilize the same CCD. With TSVs and hybrid bonding, we can increase the interconnect density by more than 15x to enable the 2 terabytes per second interconnect bandwidth in an extremely small die footprint and still allow good efficiencies for the non-stack products. Let's take one more look at this elegant engineering feat that our AMD team has achieved. The 3D chiplet architecture has been carefully engineered to enable the highest bandwidth at the lowest silicon area using the direct copper-to-copper hybrid bonding technology, plus TSVs for the die-to-die communication. The architecture and silicon floor plan was also carefully engineered to enable optimized thermal performance. As an example, we designed the 3D 64 megabyte SRAM over the SRAM cells on the CCD to keep thermal density low over just L3 on CCD and avoided overlapping on the CCD. We also enabled structural silicon for heat escape from the higher density cores or CCDs, illustrating how 3D can be done in a thermally friendly manner. AMD's 3D architecture is enabled by a novel process called hybrid bonding, which we developed in deep partnership with TSMC, leveraging their 3D fabric technology discussed earlier in this tutorial. Hybrid bonding is fundamentally a two-phase bonding approach. The first phase is where the initial hydrophilic dielectric to dielectric bonding is created at room temperature followed by an annealing step, wherein activated dangling bonds of functional groups are covalently bonded. The second phase is a direct copper-to-copper bonding enabled by the same or a subsequent anneal step, and the copper bonds are formed by solid-state diffusion. Now, we compare AMD's copper-based 3D architecture versus the current best-in-class solder-based microbump 3D architecture. Solder-based microbump technology with tall TSVs is based on traditional solder-based packaging technologies and can scale from 50 micron to 36 micron pitch, maybe a bit lower, and is appropriate for low bandwidth applications. AMD's 3D chiplet architecture, as shown to scale relative to the microbump technology, by contrast, uses silicon fab-like manufacturing methods with back-end design rule-based TSVs, with copper-only interconnects without the presence of solder. This is a transformational point in the industry's advanced packaging journey, where interconnect technologies are now being enabled using silicon fab-based techniques to enable extreme bandwidth architectures. As a result of the extreme scaling, we are also able to achieve more than 3x higher interconnect energy efficiency, more than 15x higher interconnect density, as well as better signal and power performance compared to microbump 3D architectures. This chart demonstrates the interconnect pitch differences between 2D C4 architectures at 130 micron bump pitch, 3D microbump architectures at 50 micron bump pitch, and 3D TSV-based interconnects at 9 micron bump pitch. Due to this higher packing density using TSVs and hybrid bonding, we can achieve up to 3x improved interconnect power relative to microbump architectures, providing the best PPAC benefits to enable high-performance computing products. Many of today's games have intense demands for the PC's memory subsystem, and they get much faster when a deep pool of memory is right there on the processor. As we continue to test our 3D chiplet prototype against a long list of games, we are seeing an average improvement of up to 15% at 1080p resolution. 15% is an entire architectural generation's worth of gaming performance just from the 3D chiplet technology, illustrating the power of advanced packaging technologies. Today's demonstration of 3D cache stacking over CPU cores is the beginning of the 3D journey. Future of 3D stacking is a function of TSV pitch and can spawn many architectural innovations, including IP on IP stacking, macro on macro stacking, IP folding and splitting, as well as circuit level slicing. 3D stacking technology progression, along with other advanced packaging technologies, will enable beyond Moore's law scaling this decade and enable complex heterogeneous integration schemes not possible even with monolithic designs. Today, we provided more details on our breakthrough 3D architecture that was announced earlier this year at Computex. With 2D MCM, 2.5D silicon interposer, and the breakthrough 3D architectures for chiplet integration, AMD's advanced packaging roadmap continues pushing the bar in the interconnect density portfolio to enable high-performance computing products. AMD's chiplet journey continues today. Combined with our industry-leading interconnect PHYs and our advanced packaging leadership will drive our HPC story forward. With silicon process slowing, advanced packaging innovations are critical to enable the future of compute, as well as developing flexible approaches for multiple product uses to deliver best-in-class PPAC solutions. And with that, I'd once again like to thank Hardships for inviting me to present our vision on advanced packaging and the countless AMD team members who have helped move these exciting technologies forward. Thank you.